I recently did a video on using Fourier transforms on audio files. And what we said in that video was that for audio files, which are one-dimensional, that you convert the data from the time domain into data which is in the frequency domain. For images, it's a little more complicated because they're two-dimensional. The data is two-dimensional. You have a width and a height. So in this case, Fourier transforms change image data from a spatial domain, rather, as opposed to a time domain with the audio. So it goes from a spatial domain to a frequency domain. So in order to keep things actually within the range of most CPUs, we do what's called a discrete Fourier transform, or a DFT. And that's just a way of making it possible for a CPU to perform a Fourier transform on an image. Otherwise, a normal Fourier transform is going to perform many times more calculations than a DFT. So using a DFT is a way to keep it within range as far as calculating, as far as CPU load, and we still get the same result. So in effect, Fourier transforms for imaging decompose an image into its sine and cosine components. So what would you use this for? Well, you would use it for image analysis. Maybe you want to take a look at an image and figure stuff out about it. This might be brightness, or this might be density or something. A lot of what we use it for is image filtering. So you can actually take an image, make an FFT, and then work on that data and then reverse it, and you have a filtered image. Image reconstruction. Here again, same idea as filtering. You go to you do an FFT on it. You reconstruct the data in that domain, and then you reverse it. And image compression. This is actually a widely used use of DFTs, especially in the JPEG format. So here's some examples. Top left, you'll see there's a statue, and converting that statue into FFT data in the middle, and then actually reversing the process, you get the statue on the right. Bottom set of images, you have this college campus. Doing a Fourier transform on that, or DFT, you get this middle image, and then to reconstruct it, you can reverse the process. So these are just some examples, and I'm going to show you this program in just a minute. So now we're going to do a demo on that program, and it's called Fourier Transform Lab. So this is the Fourier Transform Lab program, and I do urge you to go out and download it. This is a student version, so it's free. They do have commercial versions, which are also worth considering. But here you have an original image, the Fourier transform, and then the reverse. So one of the interesting things about this program, it's hard to see. It doesn't look like there's much except a little star in the middle, but you can actually increase the visibility of all this data. Okay, it just helps you see it a little bit better. So you can actually filter the data, and let me provide a low pass filter. And what that does is it shows you that the Fourier transform data is different, and then the reconstruction is also different. So in my learning, I learned how to do a low pass filter on normal RGB, or here it's grayscale data. So you can do that. You don't have to do a Fourier transform first. However, it makes it easier and better if you do a Fourier transform, act on that data, and then do a reversion. Anyway, this is a nice program, and I just thought I'd show it to you. So now we're going to take a look at some code, and I'm going to use one of the Intel samples. What you're going to notice is how easy it is to do a 2D Fourier transform. Under the covers, obviously, there's a lot of very difficult math going on here. But this is an Intel sample, and what they're doing is so at first glance, you see that you can either act on double data or integer data. And that's why the ifdef is here, because this program can run either for double data or integer data. Pretty simple. You just initialize all your data. And here, the math kernel library will develop an FFT plan. You've got to do that. That's always what you first do. And finally, here's the line of code that does the DFT. Okay. Since the plan actually allocates a lot of memory, you have to destroy the plan, otherwise you're going to have a memory leak. This is a scaling value. And here's where you can actually reverse it. Notice that up here when we first did the FFT, it's a forward. Now this is doing a backward, which is going to go from the FFT data back to normal. Image data, here's where it actually does the job. This is just some debug code. Finally, you destroy the plan. Really pretty simple and straightforward. And I do encourage you, I think there's a downloadable version of MKL, and I do encourage you to go ahead and download it and try to use it. So in conclusion, Intel's math kernel library makes doing 2D Fourier transforms really easy. I remember once in my Computer Science 2 class, I taught my students about Fourier transforms. We actually went through the code. Fourier transforms require differential equations, which is actually past Calculus 3. So it's quite gnarly if you do it yourself. If you use Intel's MKL, though, it's a piece of cake. You can use it for advanced image processing, for compression, and so forth. So anyway, I think it's great, and I love it.